Okay, and we're live. All right. Welcome everyone to our 245 or 345 section. Let me cover a few details before we talk about new stuff. There's still one student who's indicated they want to take the exam, so that's scheduled for Friday. As soon as that student is finished, I will open up the answer key and you can look, see what you got right, what you got wrong. One more time, it was really good effort on that exam. On activity 18, let's just do pages 1 and 2. Page 3 was a problem that we went over right before the last exam. I sort of moved it from before after the last year I had it after the third exam. This year I covered it before, so it's one of those optimization type problems. So don't worry about that one. Let's just make sure you understand the basics of antiderivatives. There will be, here's what's coming up. There will be a new video. I'm hoping that that's ready tonight. I might have to go on till tomorrow, but there will be a new video. There will be a new MyLab Math, and there will be a new activity. All that will become activity. All that will be coming up either later tonight or sometime tomorrow. Activity 18, if you've noticed on the submission, that's due right at the start of class on Thursday. We went through most of it in my 215 class, at least the more difficult problems, and it didn't take very long. I'm hoping that everyone's in pretty good stead as far as that's concerned. So that's what's coming up. We will have a quiz coming up Thursday at the end of class. Let's see, this class runs 3:45 to 5 o'clock. So we'll be back with the regular quiz schedule. The quizzes each day will be at, I'll open those at 4:50, so the last 10 minutes of our class time. That's when I'll open up quizzes for this section. If you're one of those students who's not being able to be with us synchronously, let me know, and I'll make sure that that's open for you when you want it to be open. But we'll conclude the last 10 minutes of our class periods each day with quizzes. The quiz that you're likely to see on Thursday will probably have 3 terms in it. It'll be an antiderivative, maybe something like that one question. I can really answer the 3 things that well, I guess there's a couple others, but basically here we have a power rule. Here we have the logarithm that's going to be the antiderivative of this, and here the antiderivative of the x. So those are the 3 things that I'm going to test you on as far as the quiz is concerned when we have that quiz come up at 4:50 on Thursday. So really now we're just right back into the pattern of what we've been doing all along. Videos, MyLabs, do the activities. If you get a chance to do those ahead of time, hey, I think that's fine. And then quizzes at the end of each class. So today, either in class or maybe you got some work done ahead of time, we'll answer questions basically on activity 18. That's what's the most pressing thing. Activity 18 is due, of course, before class on Thursday. And one more time, if you'd be so kind, activity 18. Again, we're only going to do pages 1 and 2. But please upload this into the assignments section. That way my partners can grade it. And you do that by taking a photo of it, saving it as either JPEG or PDF, and then either emailing it to your computer or copying it down from the cloud someplace, uploading it into the assignment section right there on Blackboard. There's a place where you can upload it and make sure that gets done. That way I can farm that little bit of the work out to my associates in the class. So with that said, hopefully I have most of the details out of the way. If you have any questions about any other details as far as how this class is going, details about how things are going in general, let me know if you have questions on the activity. That's where we can spend the rest of our time. I'm here with you until right around 5, or until the last question is answered for the day. I'll definitely stick around probably most of it, at least an hour. Okay, so we don't have to do question 4. Nope, Carson, you don't have to do question 4. That was something we covered on that last exam. If you want to practice it, hey, there's nothing wrong with practicing it, but no, it won't be due. Do we have a quiz today? No, no quiz today. The quizzes always follow the lesson from the previous activity. So since this is our first activity, since the last test, there's really nothing to quiz you on. I want to make sure everyone understands activity 18, and then we'll quiz over activity 18 at the end of class on Thursday. Do question 3, sure, Matthew, we can do question 3. That's the most difficult of all of those on this activity, I thought. So it makes you think a little bit about what's the marginal cost, how does that relate to a cost function, and what does that crazy initial condition give us? So I'm going to switch screens here for a second and get another close look at it. Suppose the marginal cost is given by, well, if you recall, marginal cost was the derivative of the cost function. Marginal cost shows you how quickly the cost is changing as you change the x, and x was the number of carriages produced each month. So as you produce more carriages, how does that affect the cost? And this one definitely should be a positive function. As you create more carriages, the cost has to go up. So in this case, it's 12500 x to the negative 0.85. And I don't care what number you plug in there for x. As x gets bigger and bigger, this cost function, hang on, yeah, this is going to be a positive number. So regardless of what number you put in here, this always comes out positive. If you wanted to rewrite this, hey, why not? Whoops, too many zeros, huh? Could rewrite it like that. Regardless of what number you put in here, remember x has to be positive, and you can't make negative carriages. As x gets bigger, and as x is any positive number, this always comes out positive. So this function, the cost function, is an always increasing function, and that should make intuitive sense. Okay, so we know the derivative of the cost function. We're also given that the fixed monthly fixed cost is 54,300. The fixed cost means this is something you have to pay whether you're producing anything or not. So in sort of math speak, we would say C of 0 is equal to 54,300. The cost of producing 0 carriages, it's still 54,300, not known as the fixed cost. You have to pay this amount of money whether or not your production line is moving. So now we want to find the cost function. Well, we're given here the derivative of the cost function. So I would think, okay, what I've learned from my stuff so far is if this is the derivative, then the original has to be the antiderivative of that. So my cost function C of x has to be the antiderivative of 12500 x to the negative 0.85 dx. So again, this is sort of a forward and backwards argument. Forward, we take the derivative. Backward, we take the antiderivative. Right, let's get our rules established on this one. I can rewrite this one, and I don't care whether or not you do this. Some people like to get the constant out front, and it makes some of these a little bit easier to look at, I think, if you do it this way, but don't feel like you have to. So I'm putting this extra step in here. If you see that as a constant multiplier and you know it just goes along, hey, skip this step. So there's our constant multiplier. Now I'm going to use the new power rule here. This is the sort of inverse of the power rule for derivatives. Everything goes backwards in an opposite order. So in a derivative, I bring the power down, reduce the power by 1. On an antiderivative, I raise the power by 1 and then multiply by the reciprocal of the new power. Now in this case, I'm not going to use C for my constant because C is already describing something else. I'm just going to use K instead. So there's some number that's added on at the end of this. The derivative of this function right here will get us back to the 1250x to the negative 0.85, regardless of what constant we have there at the end. So we're going to do a little multiplication here. We're going to take 12,500 divided by 0.15. And I remember this from the 215 class. So now I'm going to rewrite this one as a nice coefficient, rounded, I think, to the nearest whole. You might want to check me on this one, but as I recall, this was 83,333.33. We'll round it to that. X to the 0.15 plus some constant k. This is my function c of x. The derivative of this is my derivative function. Right. Now what I can do, since I'm given, this is known as an initial condition, initial because x is equal to 0, that's what was there at the very start. But with this initial condition, I'm allowed to use this to help me calculate the value of k. It's not necessarily that I have initial condition, I just need some condition. I need to be able to say when x is some number, the functional value is something else. As long as I have an ordered pair someplace on the graph, I can figure out what that k is. So let's use the fact that c of 0 is 54,300 to solve this equation for k. So I'm going to plug in the numbers as they're given to me. 8333 times 0 to the 0.15 plus this unknown k has to equal, when I plug in 0, I must get 54,000 back. Actually 54,300 is close. 0 to any power is 0, so this thing disappears. That's just 0. And I can see then that k is equal to 5,400. So now I have a cost function. Cost functions all the way worked through onto part B. So that's circled there and that. What's the total cost of 300 manufactured each month? Well, that should be fairly straightforward. C of 300, plug 300 in here, tell me what you get. If someone wants to do that, we can compare answers. I didn't do that in the first class, but if someone wants to, we can make sure that we all agree as far as our calculator work is concerned. And then part C, how quickly is the cost increasing? This function gives us the cost. The derivative tells us how quickly it's increasing. So this will be so many dollars, right? That's the total cost. This will tell us how that cost is increasing as we manufacture more carriages. So to answer part C, I'm going to look at the derivative of the cost function, the marginal cost function. Plug in 300 there. So 12,500 times 300 to the negative 0.85. And then recall what those units are going to be. This is how quickly the cost is changing. Cost is measured in dollars. The X is measured in number of carriages. So the how quickly is that is changing? Whatever number you get there, dollars per carriage produced. So if someone wants to throw up the numbers for those two, maybe a couple of you, we can get that checked as well. Oh, how to get the x to 0.15? Sure. I brought up, I increased the power by 1, so negative 0.85 plus 1. And Matthew says 25,358. Someone wants to. 250,000. There we go. That looked a little weird. $250,358 for the first one, and $98 per carriage for the last one. I'll let you tell me whether or not that's right. So if someone else wants to run through those numbers, see if they get the same thing. It seems to be right on as far as my quick mental math is concerned. Okay. So there we have it. Question 1, question 2. Okay. Thanks, Carson. So I guess next question could be, what's it going to cost to build 301? Well, it's about that many dollars plus another 98. So yep, we're settled in on that one. We know what the cost of manufacturing 300 is, and we know how quickly that cost is increasing. So that's problem 3, all the way from the beginning to the end. Let me go back. Oh, question 2. Sure, let's go to question 2 next. Now notice on this one, we had initial condition, and this is so easy to mess up. On this one, we had the initial condition there, and that really ended up just being our value for the constant at the end. Now, that's not always going to happen. You got to be really careful here, not just automatically write it down. I remember a question on the final exam pretty much every semester since I've been teaching the class. There'll be a question like that with an initial condition, and the initial condition number isn't always the number added on. So we have to be really careful. We have to understand exactly what we're getting with the information given. So if I move back now to problem 2, I can see a lot of similarities between that one and the one I just got done. Looking at problem 2 for just an instant. We know the function is given as an antiderivative, and we're given again an initial condition. So the function in question is the antiderivative of 120 e to the x dx. Much like on the previous problem, the cost function was the antiderivative of 12500 x to the negative 0.85 dx. So we knew what the derivative was. Now we're going to come back and capture the original function. Initial condition given, f of 0 is equal to 25. So now we need the antiderivative of this. Again, just for simplicity case, I like to get the number out in front first. And then I ask myself, well, what's the antiderivative of b to the x? Now, that's one of the most straightforward ones we ever get, isn't it? So this is 120 e to the x plus some constant c. So there's my f of x. Now in the last case, c just happened to be the initial condition's answer. In this case, it isn't. So let's work through this. We know that f of 0 is 25. So when I plug in 0, and I'm going to do it, I know that answer must be 25. But when I plug in 0 on this one, I don't get 0. On the last problem, when I had x to that power, I plugged in 0, I did. That allowed me to just have that constant pretty well given. Here I don't. This is not 0. In fact, this is 120, e to the 0 being 1. So 120 plus c is 25. Solving for c, it looks like c would be a negative 95. After one more step of algebra or two, c equals negative 95. So now I can go back and highlight my work. I'm just writing the whole thing over again. I've now determined what c value is, minus 95. And I always like to step back at the very end of this one and make sure I have it right. So first off, if I take the derivative of this, does it get back to where I started on this problem? Yes. And if I plug in 0, will this whole result be 25? Well, if I plug in 0, I get e to the 0 is 1, and sure enough, 120 minus 95 is 25. So those two pieces that I needed to make sure were true, I've just done my work and I've made sure they're true. I had a question earlier, and it sort of caught me a little off guard, and it was after I ended the live stream. Okay, so we got to read through the chats here. I was busy looking at the other sheet. Can you do one with natural log and absolute value? Sure, I can do one of those. And I'm also going to mention quickly problem letter G. I know I talked about this a little bit in the review session yesterday, but not everyone was at the review session. So I should have mentioned this a little earlier. The dx versus the dt versus the dy, that really just tells us what function we're working with. So on problem 7G, we had 7/6. I might as well work this all the way through. 5th root of t cubed dt. So I had a student at the end of the last class ask, well, what's the difference between a dx and a dt? And there is no difference. This dt just indicates to you that t is our variable. Those two variables need to line up. If you were to take a more in-depth calculus class like analytic geometry, calculus 1, for example, there'll be cases, or maybe higher level calculus, there'll be cases where you're going to work with more than one variable. So not in this class. In our class, all these will always line up unless I've made a mistake either writing a question or copying something down. So this just tells us that we're going to use t for the variable instead of x. If I wrote it this way, that would be incorrect writing on my part as far as this class is concerned. If this were a higher level calculus class and I take the derivative of this with respect to x, I just treat this as a constant. Don't worry about that. We're not going to throw any of these things at you. We're just working with single variable calculus here. So if I'm going to do this one, I'm going to, and here's where I think writing the constant out front really helps. 7/6 is a constant multiplier, even though there's not a multiply sign there. Let's rewrite this one then. Let's see, it's positive exponent because it's not in the denominator. 3/5 dt. And again, those things have to align. Here's one thing that students struggle with a lot. When do you get rid of the antiderivative sign and when do you get rid of the dt? So let's get used to doing that at the same time. So this was just a rewrite step. I don't get rid of this thing and I don't get rid of this thing until I actually use the antiderivative rules. As soon as I'm applying one of the three antiderivative rules, that's when I get rid of those. So I'm ready now to apply the rules. 7/6 is 7/6. I'm going to keep the t and raise the power by 1, and then multiply by the reciprocal of that new power, tack on some constant at the end. So as soon as I applied that antiderivative rule, that's when I lose my dt and lose my antiderivative sign. Okay. So now to make sure this looks nice, there's no cross canceling that can happen. So it looks like 33 5/48 fifth roots of t to the 8 plus c. So now we want to look at one with natural log and absolutes. Sure, why not? So remember, if we have y as the natural log of x, when we go to take the derivative, y prime is just 1 over x. Now there's a difference between these two functions, especially in the domain. If you recall back when we were talking about the natural log, I was asking you back on the algebra stuff what it meant. Natural log of 2, for example, means e to what power is equal to 2. So, and I can answer that when I can figure out what that power is. But if I ask you what the natural log of -1 is, you'd have a lot of trouble. You'd be asking e to what power is a -1, and that doesn't exist. So I can't plug a negative in here, and I can't plug a 0 in here either. So my x here has to be a positive number. However, x can be either positive or negative in this function. So if I'm starting with this function and working backwards, I want to make sure those domains line up. And it just so happens that if I slap a set of absolute values around it, then everything works just the way it should. So here's the straightforward one. If I have antiderivative of 1 over x dx, that's going to be the natural log of the absolute value of x plus c. So now back to this one. If I have y as the natural log of the absolute value of x, then y prime is 1 over x. No matter what number I plug in here, this function will give me the slope of that function. Again, we don't use natural log absolute values very often, but we have to be able to come up with a function that makes sense mathematically. That's why we slap the absolute values around it. Okay. So that's how those things go. And it's the one case where the power rule doesn't work. So if I was asking you this one, for example, this causes a lot of confusion in this class. We get so used to the power rule. And here's how you know you screwed this one up, right? So if you try this one by the power rule, you get x to the 0, you raise the power by 1 over 0, and then you say, uh-oh, 1 over 0, that's one of those things that can't exist. So this is the one and only case where you're starting with an antiderivative of x to a power where the power rule doesn't happen. So how else can I disguise this one? Well, really not too many other ways. Let's see if I could write a couple up here that, once you get used to seeing them, they're going to make a little more sense. So maybe I have, say, 4 over x dx. If you wanted to, you could rewrite this one as 4. There's my multiplier, antiderivative of 1 over x dx, right? That's 4 times 1 over x, multiply the numerators, and we have 4 over x. For natural log absolute value of x plus c. That would be the antiderivative. Other ways of disguising it, I suppose it could be a more complex fraction, 7 over 3x dx. But again, notice when there's x and it's to the first power and it's in the denominator. If I wanted to, I could deal with that constant first. And think about that for a second. If you multiply that constant through the front, through that fraction, again, the 7 and the 3x happen when they need to. So 7 thirds natural log absolute value of x plus c. One more way of sort of disguising it takes us back to what I mentioned just a board or two ago. Let's say we have the antiderivative of 8. We'll change variables a little bit. 8y to the minus 1 dy. This is one where you might get caught up a few times until you absolutely see this. Notice my dy and y line. 8 natural log absolute value of y plus c. Okay. Hopefully that took care of all of them that have a natural log in it. That was a nice little list. So any more questions on that? Any more questions on any of these questions on the activity or questions in general? Happy my supply of markers came in just at the nick of time. They came in, I think, no, well, I guess they're here yesterday. Evidently, these are refillable. They sent me a couple bottles of ink, so it's going to save the plastic a little bit. One H it is. A couple of things to notice on this one. The first thing is the plus sign staring at us. So that allows us to write this as two separate. The plus and minus rule apply on this as well. So I could rewrite this as 12 e to the x dx. Make sure you write the dx after that, plus the antiderivative of 6 over x dx. Now, if you wanted to, you could have got the coefficients out in front right away. 12 multiplied by e to the x dx plus 6 antiderivative of 1 over x dx. Now I'm not going to make you write that step or that step. Some of you can look at this and go right, straight to the antiderivative, and hey, if you can do that, that's great. So there's a 12, it's a constant multiplier, keep it along. The antiderivative of e to the x is still e to the x plus 6, okay? Constant multiplier, antiderivative of 1 over x is natural log absolute value of x plus c. The beautiful thing about these is you can check your work so easily. The derivative of 12e to the x returns us back to that 12e to the x. The derivative of 6 natural log of x is 6 times 1 over x is 6 over x. And the derivative of every constant is 0. So I've not only worked it forward, but I can also work it backward, or maybe you consider this working it backward, and then I can work it forward. I'm taking the derivative. Anyway, it's nice to be able to practice both simultaneously. We're going to have to use that skill of going both forward and backward a little bit on the test coming up, and certainly a lot on the final. So I'm going to have you do your work, not on this activity, but as you go forward, I'm going to have you do antiderivatives and derivatives on a number of the problems. So there we had number 1H, and I already did number 1G. So it looks like if there are any more questions, they're pretty well going to be on problems on page 1. Yeah, Brian, I talked at the start of class today that we're not going to do problem number 4. Okay, problem number 4 is one we did heading into the last exam. So if you look at the previous activity, it was on there. So I'm not going to spend any time on that one today. A little later, if you want me to, I'd be happy to discuss that one with you if you'd like. But we're only going to turn in pages 1 and 2. Maybe at the end of the hour, if there's no other questions from page 1, I'd be happy to go through that one. It's a nice optimization problem. But for right now, I'm going to spend the next several minutes until everyone is done with the first 2 pages. So just pages 1 and 2 get turned in on activity. Number 18. I think I'm through this list pretty well, yeah. So I'm ready. Next question, if you have any more. If not, I'll stick around here for a while. I know not everyone logs in all at once. I'll stick around probably till 3:45, maybe walk out and get a little drink of water or something in between. In the interim, why don't I go ahead and do that last one. So if you are interested in problem number 4, I'm going to put it up here on the board. Okay, so we need 120,000 square feet. So the dimensions have to be such that the length times the width is 120,000 square feet. The sides and the back only cost 300. The front costs 450. So this is the expensive. That's 450 per foot. The other sides are only 300 per foot. So that side, that side, that side. Part A, set up the function of the shell if the front and back are 300 feet. Okay, so initially, this is 300, this is 300. We need to get the 120 total square foot out, so this times that has to be this. That forces this side to be 120,000 divided by 300, which is exactly 400. All right, so now I'm going to price all of this out. I'm going to price the front plus the back, plus I'm just going to calculate one of the sides and I'm going to double one of the sides. Okay. The front is 450 per foot multiplied by 300 feet. The back is, what was that, $300 a foot times 300 feet. And the sides were, there'll be 2 of them, 2 of those sides. They are $300 a foot, and each of those sides are 400 long. So that's how I would calculate it if I knew what one of those dimensions was. If I don't know, then I'm going to use my variables to help me. So if we make that bx, then this other side has to be 120,000 divided by x. So now I'm working with this rectangle. What's the cost for the front? Well, $450 per foot times x feet. What's the cost for the back? It's still x feet long. It's $300 times x. What are the cost of the sides? Well, there are 2 of them. They're $300 along a piece, and I'm sorry, they're $300 per foot a piece, and the length of those sides is 120,000 over x. So you might be able to see how those 2 things compare. 450 times the length of the front 300 times the length of the back, 2 times $300 per foot times the length of the sides. So the function we want to maximize here is 750x plus whatever that comes out to be. Let's see, 600 times 120,000, 1, 2, 3, 4, 5, 6 zeros, 72. So there's the cost function that I want to maximize. I am given some constraints on this problem. The constraint is that the front must be 300 feet long. X must be bigger than or equal to 300. Let's see if we can let's see if we can minimize this cost function. We want to get it done with as little cost as possible. C prime of x is 750 plus. Now remember that this is 7, 2, followed by all those zeros times x to the minus 1. So take the derivative, we bring that power of minus 1 down. Keep our 1, 2, 3, 4, 5, 6. Keep that, and then again, this is 7, 2, followed by 6 zeros, x to the minus 1. Bring that power down, reduce the power by 1, which makes over x squared. If we set that equal to 0, we have 750 is 72 followed by the 6 zeros, I guess, over x squared. Multiply both sides by x squared. 750x squared is 72 followed by 6 zeros. Divide both sides by 750 and then take the square root. That will give you an x that minimizes this cost function. If that number is less than 300, then that's not going to work. If it's bigger than 300, then we'll be just fine. So again, this is a problem that worked a lot like the inventory cost problems worked on that last exam. And I did do a problem just exactly. I think the numbers were the same except for the cost of the sides back on activity 17. So there it is, in case you're interested, right? So I'll let you, figure out the rest of this one. X is the square root of. Okay, so if any of you want to throw an answer up on that one, hey, that'd be fine. If you have any other questions on anything else regarding class in general or activity 18, give me a message and I will answer those. Let's step, I'll get a quick drink of water. I'll be right back.
Yeah, I think this is probably I think it's helpful that I was last year. That seems more, I think the ethics is more the parts of the UNA technical guidelines. Yeah. And basically something there. So I'll go ahead and
309. Yeah, that seems reasonable. I guess I have a calculator on my, I don't know if it does square roots. I think I get the keystrokes wrong. Yep, 310 it is. Yep. So rounded to the nearest foot, that would be 310. So let's see, we'd make this 310, that's bigger than 300. The other side would be whatever this 12,000 divided by 310 is. That would get us about the right size building, so 12. It's 120,000, I'm pretty sure it was. Yeah. So 120,000 divided by 310 about makes this other side right at 387. One F. I don't know if we did for one F. I don't think we did. In my other class we did. Nope, one F is a good one to look at. That's probably, as far as the power rules are concerned, one of the more challenging ones. And the challenge is always just in the algebra, maybe a little bit on the arithmetic that follows after that. But it's understanding what the symbols measure, how they go way back to the start of January when we were debating on how to do some basic algebra identities. Problems like I did those just because problems like this tend to be a lot easier once you understand the definitions. So here we're starting out with 8 over 3 cube root of x squared dx. Now I'll go through this in a number of steps. I have a constant that I'm probably going to bring out. There's the 8 and there's the 3. I could think of this as 1 over then the cube root of x squared dx. I could rewrite it that way. That way at least the constant is factored out. And you can check your work. If you multiply back through, do you get that? Well, 8 times 1 is 8. 3 times that radical is 3 times that radical. Now we have to be able to use the power rule on this one, so we have to write this as extra power. There is no quotient rule for taking a antiderivative. So I'm going to write this to the correct power. Let's see, it's in the denominator. Since it's in the denominator, I know it must be negative. It's inside a square root or a root sign, so I know it must be a fraction. Negative 2/3 dx. Now it's set up where I can take the antiderivative. I keep the 8/3 because that's a constant multiplier. I'm going to give myself a little space, keep the x, raise the power by 1. Negative 2/3 plus 3/3 is 1/3. Multiply by the reciprocal of this new power. The new power is 1/3. The reciprocal is 3 over 1, or just 3. And then add on the c. So I obeyed the power rule. I did what I was supposed to do. Now let's make this make sense. 3's cross cancel. So if I wanted to write this in the most succinct form as possible, I would rewrite this as 8 cubed roots of x plus c. And again, if you want to check your work, you could take the derivative of that, starting with 8x to the 1/3. Applying the derivative, keep the 8, bring the power down, keep the x, reduce the power by 1, and sure enough, it works its way backward as well as forward. So there's number 1f. Well, typically the trickiest part about antiderivatives is using the substitution rule. The course coordinator, since we did move everything on off campus in more virtual situation, she thought it would be wise if we were to cut some topics out. And she suggested the topics we cut out would be antiderivatives by substitution. After that, probably the applications are the most difficult, and getting the units right when we get into word problems. So we're going to come up with what are known as definite integrals. They're going to represent something on the graph, and you're going to have to be able to understand what they measure and what units they measure as well. I think that's probably even more difficult for many students. That was more difficult for them to understand than integration by substitution was. So I'll, one of the benefits we had in this class is we learned a lot about units early on. We did a lot of units on that algebra test in the beginning, and I found that that's really paid off as we march through this. I'm seeing a lot fewer units mistakes and a lot fewer algebra mistakes this semester than I've seen in a number of semesters. So once we get into the units, I think I'll have to look ahead a little bit. I'm going to have to manipulate a little bit of the stuff coming up. The videos I've done in the past, you probably noticed that some of these have been recorded a couple of years, maybe even 3 years ago. But since we're no longer doing the integration by parts, I'm going to have to modify some of those a little bit. So I'm not exactly sure what's coming up tonight, as a matter of fact. Typically, we go straight from this into integration by substitution. What I'll probably do, if there's anyone interested, I'll probably put those integration by substitution videos up so you can watch them if you really want to learn how to do it. But I won't require those to be viewed, and I won't have any problems that look like that. So one more time, we will be back into the quiz mode every class. So we'll have a quiz on Thursday. Thursday quiz will be what's on activity 18, the one we're doing right now, right? And the Thursday quiz is going to look something like this. It'll probably have a radical in it someplace, maybe 3 over 2 4th root of x, plus maybe something like a 7 over x, and then we'll put a minus in there, minus 8 e to the x dx. So it'll be one problem long. It'll look something like that. Really, that one question tests almost everything we did on activity 18. Here's one where you'll have to use the power rule. Do a little symbol manipulation first. Here's one that you should see to be the natural log, and then the antiderivative of e to the x is e to the x. So one problem like that really allows me to test it, virtually everything that you needed to know for today's stuff. And I'll open that up at 4:50 p.m. So the last 10 minutes of class that we've always been doing from pretty much the first day on. We'll have a quiz each day. So if you weren't able to last time, make sure you understand how to submit these activities to the assignments part on Blackboard. I've been told it's fairly easy. Take a photo, save it as a JPEG or PDF, email it to yourself or put it in the cloud someplace, and then move it from there onto the place where you submit that assignment. So any more questions? Fire away. Remember on the view, okay, yeah, on the viewing guide. I did this one yesterday. That was a really good one to ask. Really, that took care of a nice little practice for Thursday's quiz, didn't it? So this one has the three parts that I'm looking for. E to the x over 7 minus 2 cube roots of x plus x to the minus 1 dx. So I'm going to try to take the disguises off of this one and make it as straightforward as possible. 1/7 is the coefficient, and that's e to the x dx. Take a deep breath and multiply that back through. Do you get that? Sure enough. Minus sign, keep the minus sign. There's a 2 multiplier, bring it out front. Rewrite this as x to the correct power. It's in the numerator, so it's a positive power. It's a radical, so it's a fraction. It is 1/3. Now the last one is sort of the one that disguises, that is in a little more of a disguise that people don't always catch. But x to the minus 1 is 1 over x. You don't necessarily have to write it that way, but typically when you see that and you're reminded of that being a derivative of something, then logarithm makes a lot more sense to most people than this one does. We're ready to take antiderivatives. 1/7, okay, antiderivative of e to the x is e to the x. And if you wanted to, you could rewrite that as e to the x over 7. So the antiderivative of e to the x over 7 is itself. The next part, keep the 2, keep the x. Raise the power by 1, multiplied by the reciprocal of the new power, plus antiderivative of 1 over x is natural log of x in absolute values, plus C. Here I could cross cancel, I guess. So that would be minus 3/2 cube root x to the 4. One thing I notice on these, either derivatives or antiderivatives, that index on the root never changes. Plus natural log absolute value of x plus c. And if I had a lot of time left over, I could check my work on that. Oh, that's the cube root. So that's one of the things that allows me to make sure when I'm writing and rewriting that I have the same problem. If I'm starting with a cube root, I'm ending with a cube root. If I'm starting with a fifth root, I'm ending with a fifth root. I always want to make sure those two align. And I find that a lot of times students can catch their mistakes if they look at that and say, wait a minute, that index on the root has changed either from a derivative or from an antiderivative. That never changes. The derivative of a cube root is a cube root. The antiderivative of a cube root is a cube root. The derivative of a square root is a square root. The antiderivative of a square root is a square root. The derivative of a fifth root is a fifth root. The antiderivative of a fifth root is a fifth root. That number and that number are always the same. Make sense? Any other questions? Okay, well, if something comes up, send me an email. My next class starts at 5:30. I'll be probably sitting down in my office getting that class ready to go. And if you want to, I've worked this with my basic algebra class a lot. I've worked with Blackboard Collaborate on little small sections. So if there's anything on here that you want to have a nice little vocal visit or work on a whiteboard, or I figured a way that you can show me your screen. So if you get stuck on a MyLab problem, for example, contact me. We can set up a Blackboard Collaborate meeting. And it's not quite the same as being right there in the same room with you, but it's pretty darn close. I found that in my basic algebra classes, it's been really, really effective. So that works as well. All righty. Talk to you soon. There will be a review session tomorrow just to make sure everything is ready to go on activity 18. I think I've scheduled that for 3 tomorrow afternoon. So if there's anything lingering on anything on activity 18 that you didn't get, tune in then. Talk to you soon. Bye.